Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we will continue with the previous lecture. In the previous lecture, let me write the topic. We discussed the thermodynamic properties of a Maxwell Boltzmann gas. Let me adjust it. Let me encircle it. Let me get my pen back. So I will write here continued. Thermodynamic properties of a Maxwell Boltzmann gas, which is the same as the ideal gas as we know it. In the last lecture, we talked about the internal energy U, then CV, heat capacity at constant volume, then the entropy S. We discussed these three thermodynamic properties in the last lecture of Maxwell Boltzmann gas. Today we will continue. So first we will discuss free energy and pressure. Free energy and pressure. Of the Maxwell Boltzmann gas, which is the same as ideal gas. Remember, Helmholtz free energy F is defined as U minus Ts. S is the entropy, U is the internal energy, T is the thermodynamic temperature. So what we do, we use the expression for S, which we derived in the last lecture. So let me write that expression. S is equal to NKB times ln Z minus ln N plus 1 plus U over T. This was the expression we derived in the last lecture for entropy of a Maxwell Boltzmann gas, and we said that it is valid for any Maxwell Boltzmann gas. Let me check this relation. S is N Kb times ln Z minus ln N plus 1 plus U over T. So we use it here. When we use it here, we put it in this expression for F, what we get, I will write directly. I will get this minus n kb t ln z minus ln n plus 1. How? I have to put this expression here. Plug the expression for S here. When you make the adjustment, you will get free energy, Helmholtz free energy F equaled minus n kBt times ln z minus ln n plus 1. Let me name this equation A, and let me encircle this equation. So this is our equation A. We will check it. Check it. Now, using Stirling's approximation in this equation A, but in reverse, using Stirling's approximation in reverse, we get that is equation A reduces to this equation. F is equal to minus n kb t ln z plus kb t ln n factorial. Let me encircle this as well. So let me name it. This is my equation B. So again, let me check it. Minus n kb t ln z plus kb t ln n factorial. So what we have done, we have used the Stirling's approximation in reverse. So if you apply Stirling's approximation in B, you will get A, right? So this is the expression for the free energy of a Maxwell Boltzmann gas or an ideal gas. Now you can see this answer, this expression for F is same as the expression for F for localized particles. Remember, we have already discussed it in the classroom for localized particles, that is distinguishable particles. F is minus n kbt ln z. This is the expression for f for localized particles. When you compare this equation B with this localized case, you see there is an addition of this n factorial term in the case of gases. This term we call n factorial term, right? This has consequences, this addition of this term. We will discuss them. First, we will talk about the pressure. So we discuss free energy. Let us discuss now pressure. We can express free energy as function of Tv and N, as you know. And when we do that, the pressure can be written as, or pressure turns out to be minus times the partial derivative of F with volume at constant T and N, right? So our pressure is minus times the partial derivative of F with V at constant T and N. So using equation B for F, using equation B for F, we get, let me write it in different color. We get P is N kBT times dou by dou V of ln Z at constant T and N. What we have done, we have simply used this equation B. So as you see, the second term doesn't contain volume, so its derivative will be 0. In the first term, Z contains volume, so we get this N kBT times dou by dou V of ln Z. Now, as you know, we have discussed the expression for Z in the previous lectures. For monoatomic spinless Maxwell Boltzmann gas or ideal gas, Z is proportional to V. Remember the equation, Z is equal to V times 2 pi m kBT by h square raised power 3 by 2. This is the expression for Z, V times 2 pi m kBT by h square whole raised power 3 by 2. So the bracket is constant. So because T is constant in our derivative, partial derivative, so Z is proportional to V. Therefore, simply this equation reduces to, let me write it, P is equal to N kB Let me write it neatly. NKBT by V. You will get 1 by V from the differentiation. So let me name this. Let me encircle it and name it equation C. NKBT by V. This is the expression for the pressure. And you can see this result for pressure is identical to the ideal gas law, which is PV is equal to RT with the constant Kb equal to R by N, the gas constant per molecule, which is the Boltzmann constant. Therefore, you can see that we have obtained the same expression for pressure of an ideal gas, same as that of the equation of state PV is equal to RT, using Maxwell Boltzmann statistics. Now, in developing Maxwell Boltzmann statistics, we defined beta as -1 over kBt and entropy as kb ln sigma. So we defined these two things this way and developed Maxwell's Boltzmann statistics. We arrived at equation C, pressure of the Maxwell Boltzmann gas, which is same as ideal gas, which is the same as PV is equal to RT with KB equal to R by N. So it simply justifies these definitions. Justification of these definitions, right? Another thing which I need to point out here, this equation C is true for polyatomic, also true for polyatomic Maxwell Boltzmann gases, not just monoatomic Maxwell Boltzmann gases. That you can check yourself. So we have discussed pressure, we have discussed the free energy. Now we will discuss another thing, that is the extensivity. Actually, what is the main thing here under this extensivity title? That is about the extra n factorial term in equation B. That is this extra term. I want to discuss about its consequences. I've skipped a page, I think. Yes. Okay. You know that for our treatments of gases or of localized particles to make sense, we require that the extensivity is correct. That means double, if we double the amount of the substance, we expect functions like U, that is internal energy, S, that is entropy, and F also to double. As long as the doubling is done at constant temperature and at constant density N over V, right? Why? Because these functions U, S, and F, there are others also, they are extensive parameters. That means if you double the amount, they should double, right? Provided temperature and density are kept constant. So whether we are talking about a localized particle or the gas, our statistical results should satisfy these extensivity ideas. Now for a solid, that is the localized particle case, let me use another color here. For a solid, that is the localized particle case, the equation is for F is minus N kBT ln Z. As I told you, it easily satisfies this requirement because the energy levels epsilon J depend only on the specific volume V by N. So when we fix V by N, we are fixing these energy levels Ej. Therefore, remember the definition of Z. Here the partition function is summation I exponential of minus Ej by kT. Exponential minus Ej by kT. So when you fix V by N, that fixes Ej, and we are also fixing T, so that fixes Z. That means at constant density V by N, N by V, when you are fixing N by V density, you are fixing V by N, that is specific volume. So fixing density and temperature fixes Z. That means Z, ln Z is constant, T is fixed, that is constant. So F is simply proportional to N. Since F is proportional to N, If you double n, F will automatically double. That means this extensivity is correct for F, right? Now, for a gas, we have that n factorial term. We will justify that n factorial term, which is additional term in the expression for F for a gas, that n factorial term is needed. Only then our F will satisfy this extensivity property. Remember, all the gas particles are competing for the same space. All the gas particles, because they are not localized, all the gas particles are competing for the same space. And we have for gas Z is proportional to V, but independent of N. But independent of N. See the expression for Z for the gas? This one. This one. So it is proportional to V at fixed temperature, but it is independent of N. Now see what will be the consequence of that. So therefore, it is Z by N, which is unchanged, when N is altered at constant density. Z by N is unchanged when N is altered at constant density. Therefore, F for the gas, which is minus N kBT times ln of Z by N plus 1. We have adjusted that expression for F for the gas. That's equation B. You can check it. It can be written this way. You can write it minus N kBT of times ln Z by N plus 1. This expression has the correct properties. Why? Because when density is constant, T is constant, Z by N is constant, then this bracket is constant and F is proportional to N as required. Right? So this has the correct extensivity property. And if there was no this additional term and factorial term in the expression for gases, it would violate this extensivity property of F. So this is this term which saves this extensivity property for gases. Next thing, we have to discuss another idea, that is the Gibbs paradox. So let me discuss. In fact, let us discuss this. Consider a box of fixed volume. So if I have a box of fixed volume, V, and temperature T. Right? So I have a box of fixed volume V and temperature T containing a mixture of two ideal gases, containing a mixture of two ideal gases. So it contains a mixture. Another gas I will represent by another color, red color. So it contains a mixture of two ideal gases, right? We name these gases as gas A and B. Let red one be gas A and another one is brown, and brown one be gas B, right? Right. Now, if the two gases are different, as we say gas A, gas B, when I say one is gas A, second is gas B, that means they are different. So when these gases are different, that is one is one and other is other, they behave independently. So when the gases are different, they behave independently. Because they occupy different states. They occupy different states. Hence, hence sigma is equal to sigma A into sigma B. S is equal to SA plus SB. F is equal to, let me define my symbols, FA plus FB, and P is equal to PA plus PB, etc. Let me define the symbols. This sigma, S, F, and P are the parameters of the mixture. That means sigma is the total number of microstates of the mixture, total number of microstates of the mixture. Similarly, S is the entropy of the mixture, F is the free energy of the mixture, P is the pressure of the mixture. So this sigma, S, F, and P are the parameters pertaining to the mixture. Parameters pertaining to the overall mixture. Right? What about this sigma A, sigma B, sigma, SA, S, let me write it in different color, blue. Sigma A, SA, FA, PA. What are they? They are the properties which gas A would have in the absence of gas B. Properties pertaining to gas A in the absence of gas B. Understand it. So sigma is the number of microstates pertaining to gas A when gas B is not present in the mixture. I should not say gas B is not present in the mixture. Yes, gas B is not present in the mixture because they are the properties of A in the absence of gas B. Similarly, SA is the entropy of gas A when gas B is not there. Fa is the free energy of gas A when gas B is not there. It is not present. Similarly, for the subscript B, that means sigma B, sigma SB, FB, and PB are the properties pertaining or parameters pertaining to gas B in the absence of gas A. Now, understand it. These equations hold true. These equations hold true. That means the entropy of the mixture is the sum of SA and SB. So it is the entropy of due to the gas A when gas B is absent plus the entropy of gas B in the when it is placed in the same box in the absence of gas A. So let me make it further clear. I have this box. It has some fixed volume, fixed temperature. I have a mixture in it. So it has now the number of microstates sigma. Now I take gas B out, place only gas A. It has entropy sigma A. Then you remove gas A, place only gas B, that is sigma B. You will see sigma will be the product of these two, and same will hold true for S, F, and P. So these equations hold. Therefore, we say the presence of one gas in the mixture doesn't affect the properties contributed by the other gas. Two gases are behaving as if other were not present. So the gases behave independently. Why so? Because they occupy different states. Now, what is the paradox now? And how is that easily resolved? And where was the issue? Now, consider the situation when the gases A and B are identical. That means you replace the particles of gas B by the particles of gas A, or you replace in the box the particles of gas B by gas A. So you have only now gas A molecules, or you have only now gas B molecules. You are making the gases as identical. In that situation, what you expect? We expect if we are putting only gas A, we are replacing all molecules of B by gas A. We expect the pressure in the mixture as twice Pa. We expect the entropy of the mixture as twice Sa. We expect similarly the sigma, as I told you, the product of when it is product, it will become square, right? We expect this as sigma A into sigma A, that is sigma A square. We expect F, free energy of the mixture, as twice Fa. We have expected the same equations will work. We make sigma B as sigma A, it will become sigma A into sigma A, that is sigma A square. We replace SB by SA, FB by FA, PB by PA, and we get this, right? Or if you are replacing gas A by gas B, then you expect P will be twice PB, S will be twice SB, sigma will be sigma B square, F will be twice FB. But what happens if you chuck it? This P is equal to PA holds true. Let me this equation holds true. But these doesn't hold. That means this is not equal to this, this is not equal to this, this is not equal to this. This is the Gibbs paradox. That what works for this mixture when gases are different doesn't work when the gases are identical. Now, where is the issue and how this paradox is resolved? This is resolved by the fact that when the gases are identical, molecules are identical, then they are competing for the states. Remember, they are competing for the states. Now, they will not occupy different states. They are identical. You cannot label them now. Therefore, they are now competing for the states. So the statistical properties of the second gas are modified by the existence of the first gas. So S, F, and sigma, they are all statistical properties. When they are competing from the states, you will not get sigma as sigma is squared, then that will impact your entropy, that will impact your free energy. So this paradox was ultimately based on what? It was based on the problem of indistinguishability. When gases are different, they are distinguishable. One gas is distinguishable from other gas because they are different gases. But when they are identical, they are indistinguishable. So gas particles, it's not one gas and other gas. Therefore, they are not going to occupy different states. There is a competition for the states. All molecules are competing for the same states. So the statistical properties of the second gas are modified by the existence of the first. This is the resolution of this paradox. Now I will give you a homework. If you take the equation we derived for the entropy, this one, S is equal to NKB ln Z minus ln N plus 1 plus U by T. Remember, we derived this expression for the entropy. S is equal to NKB ln Z minus ln N plus 1 plus U by T. We derived it for the Maxwell Boltzmann gas, and we said it is valid for any MB gas. Remember, in this expression, we have taken into consideration the indistinguishability of gas molecules. So this can guide us. What you do from this expression, you prove that S, we consider this mixture situation, you will see this S is 2SA. We expected it should be 2SA, but it is not equal to it. It is 2SA minus NKB ln 2. What you are doing, you are taking the first entropy of a mixture, then you have to take the entropy of one gas, then you make both gases same, you make B molecules A molecules, then SA is representing the entropy pertaining to gas A when gas B is absent. As I told you, you will get this result. You will see the entropy of the mixture is not equal to SA. It is 2SA minus NKB ln 2. Remember, this N here is the total number of A molecules. This N here, let me write it this way, is the total number of A molecules. You are making all molecules your A molecules. So you can see, as entropy is the measure of disorder from this expression, you are seeing this disorder or degree of disorder is lessened by the competition. If the molecules are competing for the states, if they were not competing, then S is 2SA, but because of the competition for the states, we get this minus NKB ln 2 term. So the degree of disorder is lessened by the competition. So your homework is to prove it at home from this expression for S. So this completes our today's lecture. Before leaving you, I will summarize the lecture. So first we talked about the free energy of Maxwell Boltzmann gas. We got this expression. Then we compared it with the localized particle situation. We said there is addition of this term in the gaseous situation and factorial term. Then we talked about the pressure. We got the expression same as that of the ideal gas that justified our definitions of beta and S. Then we talked about the extensivity, and we said for a solid this equation satisfies the extensivity property of F, and in case of gases, n factorial term is needed for F to satisfy the extensivity. Then we talked about this Gibbs paradox, and I gave you the homework. So this is all for today. Don't forget to like, let me write it, like, share, and subscribe my channel. You can give comment in the comment box. Thank you. Assalamu alaikum.